Awesome. Welcome back to the second day of our Kaggle Generative AI Intensive course. We're really excited to have you, over 250,000 developers worldwide, here to learn today all about AI, about the Gemini models, about AI Studio, about Vertex AI, and all of the other great products that Google has been releasing over the last several months. We're overjoyed to see the responses in YouTube, Discord, and all of the places. And we can't wait to tell you today all about embeddings and vector databases. So just as a quick reminder, our course overview, this is a 5-day generative AI intensive course brought to you by the Kaggle team in collaboration with Google Cloud and Google DeepMind. It is a kind of a very quick round trip through all of the things that you might have heard about in the generative AI space. And today we are on day 2, embeddings and vector databases. If you would like to learn more about foundational models and prompt engineering, please refer to all of the content that we shared yesterday, as well as the YouTube recording. You should be able to access both of those through all of the content that we've shared on Kaggle. My name is Paige Bailey. I lead developer relations engineering at Google DeepMind. As a quick reminder, the content that you should have already been referring to are the summary podcast episode, which was coincidentally generated by NotebookLM. We'll be talking to the NotebookLM team a little bit later this week. The Embeddings and Vector Stores Databases white paper, as well as a few codelabs on Kaggle that Anant will be going through later in this section. And to give a quick overview of the white papers, I'm now going to hand it over to Anant after quickly thanking all of our wonderful moderators. If you see them on Discord, they are working tirelessly around the clock to answer your questions, to make sure that you have everything that you need in order to be successful for the course. So please give them a lot of emoji love and say thank you. I especially want to call out Brenda Flynn, as well as Kenjal. They have been kind of doing all of the production and stage management behind the scenes, and they're really making this course happen. So thank you so much to all of our wonderful moderators. And with that, Anant, do you want to take over the quick curriculum overview?
Sure thing, Paige. Hi, everyone. It's me again to give you an overview of what we are learning together, what we learned today in today's white papers, to kind of set the stage for the Q&A session, which a lot of good questions you've asked as well. So today's white paper, day 2's white paper, was about embeddings and vector databases. And roughly, we started off by seeing, with learning about embeddings, what embeddings are, how they're useful. And we learned that they are basically numerical vector representations of data, let's say text, images, and more. They map diverse data into common semantic space where distance can be used as a proxy for semantic similarity. Now, this is great for comparing different pieces of data, or even the same pieces of data efficiently, or same or similar pieces of data efficiently. And they can also be used as a rich semantic representation for downstream models, tasks, and applications. We also looked at the various types of embeddings, such as text embeddings, which evolved from early methods like word2vec all the way to context-aware models like BERT and the Gemini backbone-based embeddings. We also have image and multimodal embeddings, plus also there are ways to embed structured data and graphs into their semantic representations. Then we looked at how training for embeddings often uses dual encoders and contrastive laws to group similar items. This is one method to train embeddings. There's also others. And then evaluating the quality of embeddings using metrics like precision and recall, as well as others on standard benchmarks, is quite important when doing so. We then looked at how we can search through billions of these vectors quickly. So hint, it's not with linear search, right? We also saw how we can use vector search with approximate nearest neighbor algorithms. Some of them, which we looked into which we read about in the paper, include SCAN as well as HNSW, which are two very popular algorithms. And these ANN algorithms trade a tiny bit of accuracy for massive speed gains. And then we also saw how these algorithms are leveraged by vector databases, which are built specifically to store, manage, and query these embeddings efficiently at scale. We then concluded the white paper by talking about applications of all of these technologies. And we looked at various things like how embeddings can be used for search, recommendations, for RAG or retrieval augmented generation based workflows together with LLMs. And we can also we also saw how the embedding part provides the context. It's used in the retrieval stage of the RAG pipeline to generate more factual and grounded answers. So these things are powerful, and we'll cover more in the code lab. I'm handing it over to Paige for the Q&A session. Take it over, Paige.
Yep, absolutely. I think that many people have had strong success using vector DBs and embeddings and setting up retrieval systems, especially for building chatbots externally. So it's great to give people the tools in their toolkit in order to do all of this successfully. And so with that, I am going to head into the Q&A. I am so excited and overjoyed today to welcome to the stage many folks from Google Cloud's Office of the CTO, as well as from Google DeepMind. I'm jazzed today to have Patricia, Alan, Xiaoxi, Howard, Andre, Chuck, and Anant to talk through some of the questions that y'all have asked, as well as to give insight into all of the awesome things that they're building with embeddings and vector databases, both in research and out in the external world. So first question is for Andre and for Howard. Creating effective embeddings is crucial, as we saw in many of the things that we were reading over this past 24 hours. What are the latest advancements or best practices in generating embeddings that capture nuanced semantic meaning, especially for specialized domains or multimodal data, which are increasingly becoming important, being able to embed things like images or videos? How much does the choice of the embedding model impact the performance of the downstream vector search task? And Andre, do you want to start?
Yes. Thanks, Paige. Hi, everyone. Thanks for the question. So to start with the advancements, a notable one recently is to integrate LLMs in the embedding model development stage, as I guess you would expect. So LLMs can be used as a pre-trained backbone to initialize the embedding model. And this allows the embedding model to already leverage multilingual and multimodal understanding and not necessarily have the embedding model need to learn multiple languages or multiple modalities directly at the embedding training stage. And the second point about LLM usage is that it can help refine training datasets with data curation or by generating high-quality training examples. So I encourage you to take a look at the recent Gemini embedding model and the associated tech report, which discusses these points in detail. Now, to talk about multimodal, specifically talking about embeddings which understand images, spatial awareness is a property that's often lacking. So for this reason, recently my team at Google DeepMind introduced a powerful new embedding to address this issue called TIPS, and this stands for Text Image Retraining with Spatial Awareness. This is a paper that we'll present later this month at iClear, which is one of the main AI conferences. So I encourage you to take a look at that too. We have code and models publicly available for this model. And to the final point in the question about how embedding quality can impact performance, this can be very significant actually. So for many applications on retrieval augmented generation or RAG, just like Anant was mentioning, having an LLM model by itself, it would simply not be able to answer questions if the right documents are not found. So this is, of course, a little bit application dependent. For example, may depend on the size of the index you may be retrieving from, or if the types of data that are being retrieved are similar to what the embedding model was trained on. So I encourage you to carefully consider embedding choice, as it could definitely be a bottleneck for AI systems today, especially given that LLMs are already so powerful. Okay, thank you.
Absolutely. And we'll be adding the links to the papers that you mentioned, as well as congratulations on getting accepted for iClear. That's super exciting. And if folks are interested in reading more about Andres and his team's work, that would be a great place to learn more. Howard, is there anything else that you would like to add?
Thank you, Paige, and thank you, Andre. Just a couple, I think Andre covered it pretty well. Just want to add a couple of more points. One is there's this technique called the Matryoshka embedding. which is actually currently pretty popular. The idea is that if you actually have an embedding space with, let's say, a dimension of 1,000, we're training, putting some training, requirement here to train an embedding which require the shorter length embedding. For instance, the first 200 floats, or the first 100 floats, to be also in the same embedding space, in that you can basically trim the embedding such that you can still perform similarity measure, and they're all valid. That way, you can decide how big of the embedding you want to store from one training, and then you can always each dimension does require to be pre-specified, but this is a pretty powerful technique for being able to efficiently represent embedding in these type of vector store database scenario. The other thing I would like to emphasize is the use of LLM for data curation. This happened in many recent papers, including the Gemini embedding paper. LLMs are really powerful, and we all know that. And then it is crucial. Right now, it provides this capability for filtering low quality examples and determining relevant positive and negative passages for retrieval, and generate really rich synthetic data set. And then one last thing I want to mention is that right now, some of the papers like EV5, they actually use multimodal LLMs to bridge the gap for input. So this is mostly used for multimodal embedding. And I think you will see that trend become more relevant. And in Google, we're also working on something like that. And then I think you will see Gemini embedding to become multimodal soon. Yeah.
Awesome. Thank you both for pushing the boundaries of what's possible with embeddings and making sure that we can get these things out into the world so others can make use of them, not just Google and not just DeepMind. This is really, really cool, and one of the most powerful ways to get research out into the world. Next question for Alan. So when integrating vector search capabilities into existing database systems like AlloyDB versus using dedicated vector databases, what are the primary architectural trade-offs regarding performance? So things like latency and throughput, cost, data consistency, and ease of use for developers who are building applications like RAG or semantic search. And also for folks in the audience who might not have heard of AlloyDB before, if you could just give like a couple of sentence description of what AlloyDB is and why it's useful.
Sure. Thanks, Paige, and thank you for the question. So my name is Alan Lee, and I'm part of Google Cloud Databases and the lead for AlloyDB Semantic Search. So AlloyDB is one of GCP databases database offering. It is fully Postgres compatible with additional innovations on the architectural side to make it faster than what is available for open source Postgres. And this allows our customers to be able to take their operational database workloads and run it faster on AlloyDB. And we've incorporated vector search capabilities in it as additional advancements for our offerings for customers. And so going back to your question, so while performance is listed first in the question and is often the top of mind metric that many think about, I do see more and more non-performance requirements from talking with various customers. And part of the shift is coming from the improvements in vector search performance of existing database systems that will generally work well for 90% of the use cases. And so as an example, AlloyDB, we've incorporated the scan algorithm as a native vector index type. And as the course participants may know from the white paper, SCAN is based on 12 plus years of Google research and is our state-of-the-art vector search algorithm that's used internally at Google scale for products like Google Search, YouTube, ads. And this algorithm has given AlloyDB the vector search performance that is more performant and scalable than what's available in open source. And it's also competitive with specialized vector databases out there. And so other important architectural consideration is that we should all be thinking about when building on top of vector search is where the other data, like what other data needs to be accessed for the overall application, and where does that data come from? So for example, filter search is a very common use case for many customers. And filter search combines a vector search query, for example, shirts that look like this image embedding, and filtering conditions, size equals small, and color equals purple, and price less than $50. Where do these other filtering condition data reside? Is it structured data that's already in an operational database, or is it in a data lakehouse like BigQuery? So if that's the case, it may be easier to leverage the vector search capability of those systems, and that will allow the user to express their vector search along with filters and joins, and in a single system and in a single interface like SQL. Otherwise, there will be additional operational overhead and costs of things like ETL pipelines and implications of dealing with data consistency issues across systems, and application complexity of having to join across multiple systems. And that's without the help of a query optimizer that's typically there for SQL-based systems. And these things make it harder for developers. Specialized vector databases like our vector search, Vertex Vector Search have their place as well. If data is largely unstructured, like video, images, and documents that don't already typically reside in a database or a data warehouse, then none of the data consistency or application complexities that I mentioned apply, and specialized vector databases can work quite well in these cases. And unlike databases and warehouses that have to generalize across various workloads, including non-vector workloads, specialized systems can squeeze out the last bits of performance, and that may matter for the 10% use case. And usually this comes with trade-offs like higher costs for purely serving out of memory, or having looser data consistency models for index writes and updates. And lastly, depending on the use case, some other important considerations include security, compliance, reliability mechanisms like backup, HA features. Just generally speaking, existing databases have more mature enterprise-grade features than specialized systems, and that's mostly as a function of how long they've been around. So it's important for the practitioners to think about like all the requirements of their entire application.
That makes a lot of sense. And I love that we've been able to take kind of this decade plus investment in research at Google and get it out into the world, into the hands of customers through AlloyDB. I'm hoping to learn more about some of the use cases at the Google Cloud Next as well. I know that many customers have been implementing AlloyDB in production and then getting serious gains from it. So thank you for the great answer. Next question for Patricia, and I believe also Alan might have some thoughts around this too. From a strategic viewpoint, how do you see the rapidly evolving landscape of vector embeddings in databases impacting enterprise data architectures and the types of AI-driven applications that businesses can build? what are the key challenges? So things like cost management, standardization, talent gaps that organizations face in adopting these technologies at scale. And in your role in the Office of the CTO, I'm sure you must see this for many enterprise customers.
Yes, fantastic. Thank you for the question, because this is a very important one. I think that traditionally we have often underestimated the depth and breadth of the impact that certain technologies may cause. And I think that we are in the middle. I don't like to call it a paradigm shift, but to offer or introduce an alternative where we are going from optimizing the indexing and retrieval capabilities of our data architecture to an exact match, like in SQL, across several fields of your structured data corpus, to being able to create several indexes of your data across multiple dimensions, to optimize how you index on a per task basis. You can create multiple indexes per database, and to search and retrieve data based on some fit for purpose metrics, such as semantic similarity for search, for example, or proximity for certain attributes in recommendation systems. And all of this in multimodal data, where one can be looking for similarities, but much more like nuances between video, audio streams, text, images, not just between concrete data points on the same modality as we are so used to do with SQL today. And this requires a paradigm shift across several dimensions. So if you look from an architectural perspective, we have to really learn or relearn how to ingest, organize, manage, make accessible new modalities of data that we have not dealt with on a daily basis as we are doing now, especially semi and non-structured data. This also includes learning the variety of indexing mechanisms, especially the ones that the Google Cloud and Google offers available to the different storage types, and also understand the trade-offs between accuracy, performance, and scalability, which I know it was in the white paper that you read. Also, from a development perspective, it demands developers to have like a deeper understanding of the meaning of embeddings, which is a non-trivial concept, as we also learned in the last day. And from an application experience perspective, we really need to reimagine the user experience that can now be offered, because you can retrieve such a complex set of multimodality data. But it doesn't come without its challenges. You have cost. The infrastructure costs associated with deploying and maintaining vector databases. Standardization, as you saw, there is a lack of universal industry standard for vector embeddings, and database interfaces poses integration and interoperability challenges. I would say the talent gap. But now we have another 250,000 people that are familiar with the concept of embeddings and vector databases. There are issues of scalability and performance, because you're really handling massive data sets with billions of vectors, while you want to maintain low query latency and a careful architecture design and selection of indexing techniques. And you add on top of that data governance, security, and compliance that cannot be neglected, and integration with existing systems, integrating vector databases with traditional relational databases and existing business applications, which can be very, very complex. However, we are very, very, very optimistic, because multimodal data representation through their embeddings in a scalable, performant, and accurately retrieved manner, we believe that is going to form the foundation of modern enterprises architecture. So thank you for the question.
Absolutely. I know that, increasingly things like video understanding, being able to have insight into all of these different modalities are super, super important. And I love that you called out that thanks to all of the folks who are dialing in, we now have over 250,000 developers out into the world who will be able to help with some of these mission critical tasks going forward. So this is great to know. Next question. This is for Chuck. Beyond standard cosine similarity or Euclidean distance, what more sophisticated techniques or indexing strategies, so things like incorporating metadata filtering or hybrid search approaches, re-ranking, are proving the most effective for improving the relevance and accuracy of vector search results in real-world applications? And how are we sort of taking all of these learnings and embedding them into platforms like Vertex AI or in Google Cloud?
Great question. Thanks for the question, and thanks for all the questions on Discord. Like, we'll try and get to them offline if yours didn't get answered here, but lots of great activities there, so thank you. I'd say, just to start off and frame that question, there's a lot there about, as you've seen in that question, there's a lot of knobs you can turn for embedding systems that can make a big difference, especially when you're doing something at scale, but they might not be necessary for your use case. And so, you heard Alan talk about the 90% use case, the 10% use case, the 1% use case. And so anybody who's talked to me is going to hear me talk about the importance of like a good evaluation suite. So if you have an example benchmark data set or something that can help you figure out whether or not it's going to make a difference for your use case to add that extra complexity. In practice, what we see people doing or being successful with, out of the things you were talking about, I would say RAG hybrid search is one that really makes a big difference. So for people who aren't familiar, this is the idea of taking what we're talking about here with the embeddings, those semantic embeddings usually, and then combining them with traditional keyword matching. So you want to be able to get it when you have something that isn't exactly the same, but is related. So a synonym, you want to be able to pick those up with embeddings. It really makes a big difference. But those traditional keyword systems, where if someone actually knows the title of the article they're looking for, or the ID of the part that they want to find, or the product, you really want to support that too. And so combining those two things in what people call hybrid search really helps. I think it's going to get more complicated as you go on, because we have people like Howard and Andre who are doing amazing work with multimodal. And so now hybrid search is going to start to include things like video and images and other things. So we'll get a little bit more hybrid-y. So just be aware for that. And you can see that in our tools. So like at Google Cloud and Vertex AI vector search, we support both sparse, which would be those keyword embeddings or keywords, and then semantic in the same tool. But you can also just pick up like BM25 in popular Python package. You can just try that out. So like if you look at code snippet 0 in the white, or code snippet 1 in the white paper, you could just drop in BM25 and do the same thing and get the same measurements for precision and recall and get a feel for how that would work for you. When you start to add additional modalities, so like if you're going to do keywords or you're going to do images, then you're going to probably want to do some kind of re-ranking at the end. You may want to do re-ranking anyways, but it's really, re-ranking is really helpful for finalizing that final list to the customer or person who's going to be reading it. And so, maybe you want to like combine a few different retrieval methods. You could just look at the ranks, or maybe you want to do something where you're actually going to rank certain documents higher. So like an official frequently asked questions document might be more reliable than something that document that you pull off of like the community notes. And so you'll see people do that, and it can be really helpful for those sorts of use cases. Just keep in mind your latency budget whenever you're doing that sort of stuff. Some of the other things that were in the question, like I would sort of qualify as ease of use and really make a big difference at scale. So filtering something can really cut down on latency if you can get rid of most of the irrelevant answers or irrelevant documents early in your process. The same thing I would say for streaming inserts. If you don't want to like rebuild your index all the time, that can be really helpful for your team. I think anytime you're picking up a new vector database, you really want to make sure that it's going to meet your company and your organization's ability to support it and maintain it. Like, is it going to be easy to use? Is it going to be easy to monitor? Does it meet your privacy and security requirements? So it's, it is a new piece of infrastructure, and you just want to be in sync with your other stakeholders and make sure that's something that your group can own and maintain and scale. Because like people were saying, this really is a key piece of infrastructure at Google, and I think it probably will be at your organization or in your projects as well going forward. So I think that covers it all. There are a lot of knobs to turn. Please feel free to ask more questions or follow-ups on the Discord, and we'll be hanging around there to try and answer things there, time zones permitting. Thank you.
Awesome. I love that answer, and I love how you're making it real for people who might be hoping to implement some of these things in production. Things like filtering and re-ranking are kind of hard-learned lessons and optimization approaches internally at Google. But I think for folks who are just starting on their journey, those are good things to call out and to have top of mind on day one. So love that answer. Next question, also for Chuck. For embedding models, this is from our Discord, Cyclone Duster, which I wonder is like Cyclone Destroyer. I'm not sure how to pronounce it, but I'm going to try my best. For embedding models, how to upgrade to the newer embedding models when they're available? Do we need to run all of the data in the database again through the new embedding models, or is there a better way to do it? So it sounds like this person is just getting started with embeddings, and they're trying to understand all of these different models that are available. How might they use them effectively?
So I hate to be the bearer of bad news, but you do have to upgrade all of your embeddings that you've done when you switch to a new model. And that's one of those things. Embedding models just aren't compatible with each other. And so that's just sort of the way the world works. I apologize, but it is like different languages or different versions. Trying to link to a different binary library that was compiled with something else. So that is the way it is. I think the thing I'm going to say again is just the importance of good evaluations. So when you're doing that upgrade, you want to be able to know that you have the matching version for whatever query you're using and whatever the indexes that you're querying. And so having a good evaluation suite really helps that. And I would say, in addition to the usual precision and recall and sort of like AI-based metrics that give you a sense of the quality of those of what you're retrieving, don't forget to be measuring things like latency and other like important system metrics like the throughput, the latency, how does it perform under load? Because you will see with these more sophisticated models, they do have a lot more parameters, and so maybe they need a little bit more hardware. But I think, and there's nothing like qualitative feedback from your users, but having a good like even a not so good evaluation suite can really help smooth that process and make sure that everything is working for you and your users as you change these embedding models. But yes, you do have to regenerate the embedding model, the embeddings for your index if you upgrade the embedding model. And I would say the way things are moving, you've got really smart people at DeepMind and in the community doing amazing work, and you're going to want to be able to pick up those changes because they really are big improvements. And so I would say just be ready for iteration. The train is moving quick. Enjoy it.
Yep, and I love that quote. The train is moving very quickly. We just released a new embedding model on AI Studio just a few weeks ago. Howard, it also did you want to add something?
Yes, and thank you, Paige, and thank you, Chuck, for endorsing our work at DeepMind. I just want to add a little bit one thing that we're thinking, leave no one behind. So the train is leaving, but we also try to get the get the passengers on this train. So this is active research area, but I think what we're really looking at is how do you think about the embeddings, the previous embeddings and the newer embeddings, and is there a more efficient way to map from previous embedding to the newer embeddings? I think in terms of ongoing research, we see fairly promising results. It's not deployed. It's I think probably many people in the research community are looking at the same problem because it is a pain to upgrade the entire database to new embeddings, especially when the new embeddings are coming every day, right? So just want to add that this is an ongoing research area. We see very promising results, and hopefully we'll see that in Google Cloud and many places soon.
Awesome. That's great to hear, and awesome to know that that folks in the research world are kind of pioneering some of these approaches to make life easier for all of the developers out there. So appreciate your response to this question too. Next question. In retrieval augmented generation, so these RAG systems, what potential impact could arise in retrieval accuracy or the quality of LLM generated responses if different embedding models are used for documents and queries? So Xiaoqi, do you want to answer this one?
Yes. So thanks, Paige. Hi, I'm Xiaoqi Ren. I'm from Vertex AI. I'm the technical manager on the Vertex AI embedding quality. So regarding to this question, it's very critical that we use the same embedding model for document embedding and query embedding generation. The reason behind that is the embedding models, they transform complex data like text, image, audio, videos into a shared vector spaces. However, this specific mapping from real objects to vector spaces are different model by model. So using the same embedding model in RAG will ensure that both queries and documents are projected into the consistent embedding space. This is crucial because the distances between the shared spaces are then used to accurately reflect the semantic relationship between the queries and documents. So please try to use the same like queries and documents from the same embeddings when you build your own RAG.
Excellent. Thank you for highlighting those best practices. And I think as many people are just starting on their journeys, those are the kind of gold nuggets that make all the difference to make sure that they get started on the right foot and in the right place. Awesome. Next question. In a RAG system, indexing is performed in advance on the application data set. So how does the system ensure that query results remain relevant to the current context in a dynamic or real-time application after deployment? I love this question about kind of system drift. Patricia and Anat, do you want to take a stab at the answer?
Sure, maybe we start there. So first of all, yes, measuring drift to see how embeddings change over time is super critical. And coming back to what Chuck mentioned, having the evaluation suite, but also to measure the drift in performance, but also general distribution drift is important. However, there's one more key point, which I think, especially in the context of RAGs or how embeddings are used with retrieval augmented generation systems, which can make this whole process more efficient, is that the process of embedding as well as embedding entire databases also depends on the dimensionality of the embeddings. So if you have a larger embedding of say 2000, however, if you consider the concept of Matryoshka embeddings, where we can trim the embedding down, and also consider the fact that you can make the whole process much more efficient, because in larger LLMs with increasing context windows, you can retrieve a lot more than just the top 10 or top 5 documents. So you do not need to necessarily care so much about the performance of the top hits at K, the retrieval performance in the top 5 items. You can afford to focus more on recall rather than precision, where a few false positives are okay, but in our increasing context windows. For example, Gemini's I think 1 to 2 million context window, depending on the model you use, allows us to use slightly less performant embeddings, but allow the indexing process to be much more efficient, because we can use embeddings of lower dimensionality. So that's one aspect to it. I believe Patricia and Alan had things to share on this.
Absolutely. No, thank you for that, Anat, because this is really, Anat brought up the issue of using the context window and the flexibility on the retrieval, allowing for false positives that can actually give a little bit more of items to be retrieved or exposed to the user. On the other side, of the equation, you would say on a complementary side of the equation, what you are trying to do is effectively bridging the gap between static index and evolving data as well. So another aspect is to say, look, the data has drifted. We indexed the world as we saw it some time back, and now the world is different. There are items that have been added and items that have been removed. And there are several strategies focused on updating the vector database and its index in near real time in response to data changes. So one technique is called incremental indexing, and which allows for the addition of new data to the index without requiring a complete rebuild. It's like adding this information, and reduces the latency and computational cost that is associated with keeping the index always current. There is always also what is called HNSW, which is the hierarchical navigable small world, which is a popular indexing structure that generally handle the insertion of new vectors more efficiently than tree-based indexes like ANOI. Research continues to advance in this field, and we should always be mindful and look at what is coming. One of them is called the advanced inverted file, which achieves higher updated throughput, I would say, by maintaining policies and local clustering. But this is not all, because of vector databases, they often employ in-memory buffers to handle new data and background processes as they merge these changes into the main index. So change data capture mechanisms actually provide an automated way to trigger updates to the vector database whenever changes occur in the source application data set. So we have to look into that as well. Continuous indexing and embedding generation can also consume significant computational resources, so we really need to be mindful of that. An alternative approach, just to wrap up, is the real-time reg or no index reg. So you don't create the index at all. It completely bypasses the need for pre-computed indexes by directly querying live data sources at the time of the user query. In this architecture, when a user actually submits a question, the system transforms the query into a format suitable for the source system's native search API and submits this transformed query to the relevant data sources. In any case, it's always important to actually achieve a trade-off between cost, performance, accuracy, scalability, and freshness of the data.
Yeah. I love that answer. And Alan, do you want to add something in addition?
Yeah, just to briefly to add on to Patricia's answer, I think an important part of operational databases is the transactional and strong consistency guarantees between reads and writes, and that includes index updates. And what the transactional semantics means is that inserts and updates that are successfully written are immediately visible for subsequent reads. And this helps developers avoid dealing with eventually consistency issues like having stale data that shows up that has to now be hidden from the user. And this is also important for some business use cases where it is important to have visibility to the latest data. So again, this goes back to considering the requirements of the entire application. And in addition to what Anant said about the data drift issues, there is also innovative work on automatically handling index distribution or drift issues to make it easier to use for everyone.
Awesome. Thank you for the great question, Prashant. As a workaround for this, I sometimes use the Google Search API feature within the Gemini APIs. So you can ground information on the latest Google search results, which sounds very similar to one of the things that Patricia was mentioning, of just using kind of a search to query the live data source and to get the response back and to incorporate that into a summary. So lots of tools in the toolkit to make sure that as you're building your outputs from the large language models or building these systems which drive the outputs, you're capable of getting the latest and greatest information. Next question from Andy G. How does the precision of a single multimodal model for image and text embeddings compare to using a separate single modal model? And this is for Andre and for Howard. Do y'all want to answer?
Yep. Do you want to start, Howard, or should I start?
Please go ahead.
Yeah. So I think the question implies that you're considering to use for a single modality search, right? Either a model that actually can handle multiple modalities for single modality search, or actually use single modality search for single modality retrieval applications. Because of course, just to make sure we're all on the same page, one of the big advantages of having a multimodal model is that you can actually retrieve, search query with text and retrieve an image. For example, if you're talking about image and text, it's two modalities, and vice versa. And you would not be able to do that. You would not be able to do that using single modality models, right? So there is already one advantage, but the other thing is that it's not necessarily that single models will necessarily be better in single modality evaluations, because, for example, when you look at specifically at image and text, there's a lot of data online, for example, that has a text supervision, text annotated together with the image. And just by learning models that way that are already going to be multimodal, you are actually able to leverage a lot of supervision, which sometimes you're not able to do if you want to have manually rated data for images, which is much more expensive. So, and the other thing to mention is, of course, many of these things depend on the model that, on the data that the models were trained, how large are the models. Generally, we see the trend in the community of going to larger models, more capable models that will do well across many different modalities, rather than having specialized model for each modality. Of course, you can also apply this technique called knowledge distillation to take a really big model, really capable one, and distill on a smaller model to accomplish a task that is a little bit more restricted, or just to have a smaller model generally. So yeah, these are some thoughts. Howard, is there anything else you wanted to add?
Yeah, thank you, Andre. And one thing that that we observe as a trend is that people are using the LLMs or multimodal LLMs as a way to bridging the gap between modalities. So, for instance, take the EV5 model. They basically have the multimodal model LLM as a way to take the input from any modality. And then what they were training is purely training on text, right? But because the ML, so the LLM has already taken care of the input modalities, so it effectively, once, by that I mean, they map images and text into the same embedding space. So all you need to do now is to organize this embedding space based on text information. So let's say if you are clever, well, you can really organize the word of airplane versus fighter jets versus aircraft carrier in a space, relatively. Then images of airplane, fighter jets, and aircraft carrier will be automatically organized because these are shared embedding space. So that technique is actually very powerful. I think what we observe is that today, so a couple of the representative models. So you have single modality models, what we call dual encoders, where you just align them for image text tasks, alignment tasks like clip or align, and they used to be state of the art. But now these single multimodal models started catching up. Examples are Kokai and then E5V. I think the trend is that we'll probably see the single multimodal models will achieve higher and higher precision and close the gap, and even surpassing the dual encoder models that uses separate single model components. Yeah.
Awesome. Fascinating. I love those answers. And thank you so much, Auntie G, for the great question. And with that, I want to give a big virtual round of applause to all of our wonderful Q&A experts who came here today, who gave their time to be able to share more about what they've learned, as well as to help answer our community questions. We really appreciate all of you and your time. And thank you so much again. The next section is going to be all about our code labs around embeddings and vector databases. Thank you so much to Mark McDonald for creating the notebooks. And Anant, do you want to take it away to explain them? Folks on the call, you can also kind of go off into the background while Anant's doing the explanation of the code labs. Thank you so much. Anant, you might be on mute. So yep.
All right. Yeah. So just to be efficient, since we had an interesting conversation, I'm going to make this section super short. I'm sharing my screen now. This notebook is RAG, Retrieval Augmented Generation. Here you will see how you can utilize the Gemini API and open source databases to build a simple RAG pipeline out. So firstly, we see in the first section of the notebook, we see how we make some synthetic data, three paragraphs. And then we, in the second part after that, we see how we use ChromaDB, an open source in-memory database, to kind of index this data and create so you have a embedding. We use embeddings to embed the text data and then persist it in the ChromaDB. And after that, we see that was the index. Sorry, that was the generation, embedding and indexing part. Then comes the retrieval part of RAG, where we see how we can leverage this database to query, take a natural language text, a query from the user, and the database internally embeds it and retrieves the top k most similar results. And then after that, we see, okay, now that we have retrieved the most similar results, how can we use that to answer the question using the Gemini 2.0 Flash LLM? And that's the last part of the collab, where we do the generation part with the retrieved documents by the semantic search. So that was that's your very basic RAG app. Now I'll move on to the second collab. So moving on to the second collab. Yeah, give me a second. Yes. So the second collab talks about exploring the semantic aspect of embeddings to see how similarly or documents with similar meanings are grouped together in the shared semantic space. So in this collab, we see how we define some sentences, some synthetic sentences, and we embed all of them using the Gecko embedding model by Google. And we see how they look, how their semantic similarities look in through a heat map. So in this heat map, you see that on a scale of 1 to 0, where the darker shades represent values closer to 1 and the lighter ones represent closer to 0, we see that documents which are more or less meaning the same have a darker shade, which means they have much more semantically similar. And of course, the diagonal represents a document being compared to itself, and a document will always be most semantic similar to itself, of course. But then we see how other documents are not very similar, and you see lighter shades there. For instance, the quick brown fox jumps over the lazy dog. This is very semantically similar to itself and a slightly misspelled version of itself. However, it's not very similar to the 5 boxing wizards jumping quickly and so on, because these mean 2 different things. So that was the collab on semantic similarity. Let me quickly go over and walk through the last collab, which you're going to see. So we talked a lot about embeddings being used for semantic search and proximate need to find similar documents, etc. But there's another very important application of embeddings, that is using embeddings as a feature extraction of sort for downstream models. And in this collab, we see exactly that. We kind of use an open source data set, the newsgroups text data set, get the train and test splits for it, pre-process the data set in the subsequent section to kind of make it nice, where each of the text, the news articles have various classes, and we are basically taking the text and trying to classify it into the right target class. So we see that if we use the embedding models to create like a embedding representation of the news text, and then train a classifier on top to tune, add a layer or 2 afterwards, and only tune those 2 layers, is very efficient, since the embeddings already carry very rich representations. We use the classification task type for the embedding models, and we add we use that to as in Keras to basically get the embedding representations for the text, and then build a classification model with that. And you see that we get pretty good performance in the task after that. And we can also try it on our own handwritten texts. So this is how you can use embeddings for downstream models and beyond just semantic search. So that'll be all. Off to you, Paige, for the next section. Thank you.
So much, Anant. And now we are going into the last and final section of today's course. We're going to be doing the pop quiz. And so our first question, which application are embeddings not the best suited for? Is it retrieval augmented generation, or RAG? Is it simple rule-based systems? Is it anomaly detection, or is it recommender systems? What application are embeddings not the best suited for? I'm going to count down. Everybody grab a piece of paper and a pencil and jot down your answer, or just type them out someplace handy. 5, 4, 3, 2, 1. And the answer is B. Simple rule-based systems are not something that embeddings are best suited for. Next question. Which of the following is a major advantage of SCAN over other approximate nearest neighbor algorithms? Is it A, it's widely open source and available? B, that it's designed for high dimensional data and has excellent speed accuracy trade-offs? Is it C, that SCAN only returns exact matches? Or is it D, that it's based on a simple hashing technique and has low computational overhead? Which is a major advantage of SCAN over other approximate nearest neighbor search algorithms? And I count down 5, 4, 3, 2, 1. And the answer is B. It's designed for high dimensional data and has excellent speed accuracy trade-offs. So hopefully you were paying attention to when Alan was talking all about AlloyDB and some of the SCAN research approaches there. Question 3, what are some of the major weaknesses of bag of words models for generating document embeddings? Is it A, that they ignore word ordering and semantic meanings? B, that they're computationally expensive and require large amounts of data? C, that they cannot be used for semantic search or topic discovery? Or D, that they're only effective for short documents and fail to capture long-range dependencies? So what is some of the major weaknesses of bag of words models? I'm going to count down 5, 4, 3, 2, 1. And the answer is A, that they ignore word ordering and semantic meanings. Question number 4, which of the following is a common challenge when using embeddings for search, and how can it be addressed? Is it that embeddings cannot handle large data sets, so you have to use a smaller data set? That embeddings are always superior to traditional search, so there's no need to kind of couple together search? Is it that embeddings might not capture literal information very well, so you have to combine with full text search? Or is it that embeddings change too frequently and you have to prevent updates from happening? So what is a common challenge and how do you address it for embeddings? I'm going to count down 5, 4, 3, 2, 1. Hopefully no one thought that the best approach was to prevent new information from happening or new things to occur. The correct answer is C, that embeddings might not capture literal information very well, and so you should combine them with full text search. Question number 5, what is the primary advantage of using something like locality-sensitive hashing for vector search? Is it that it A, guarantees finding the exact nearest neighbors? B, that it reduces the search space by grouping similar items into hash buckets? C, the only method that works for high-dimensional vectors? Or D, that it always provides the best trade-off between speed and accuracy? What is the primary advantage of LSH for vector search? I'm going to count down 5, 4, 3, 2, 1. And the answer is B. It reduces the search space by grouping similar items into hash buckets. So thank you so much to everyone. Hopefully everybody got 100% correct on the pop quiz. And we will see you tomorrow, where we're going to be doing the next instance of learning for our Kaggle Generative AI intensive course. Really jazzed to see what questions you might have over the codelabs, the white papers, and the podcasts over the next 24 hours. And see you all tomorrow. Thank you so much.